Hi, welcome back. This is week 3 lecture video. We'll talk about derivatives of exponential functions, product quotient rules, and some trig functions, as well as the chain rule. Okay, so let's go to the random video again. Okay, so the first rule we're going to learn today is the exponential rule, which is that when you differentiate e to the x, this is one of the simplest rules that we will learn, the derivative is actually the same as e to the x. So this is the only function where when you differentiate it, it stays the same. All right, here's an example. Let's say that we have the function f of x, which is e to the x minus x, and we want to find the first derivative and also the second derivative. Okay, so again, we learned about the sum rule earlier, sum and difference rule, which is that if you want to differentiate e to the x minus x, which is the difference, you just differentiate them separately and then subtract them. So the first part is differentiating e to the x, and then we differentiate the x function, and then you subtract them. But differentiating e to the x is very simple, it's just e to the x. And then differentiating x, we learned this last week, just the power rule. Again, take the power, bring it down, subtract 1. But this is the case where you should remember that if you differentiate a linear function, the derivative is just the slope, which is the number in front of the x. So in this case, it's just 1. So it's e to the x minus 1. Again, whether you use the power rule or just realize that the derivative of the linear function is just the slope of the linear function, the answer is going to be the same. And so in this case, it's just 1. And then to differentiate it the second time, you just simply differentiate the derivative. So you differentiate this, and so that this is called the second derivative. And so again, we just differentiate ex, and then you differentiate the 1, and then you subtract them. And differentiating e to the x is just e to the x, but differentiating a constant, the derivative of a constant, is just 0. And so this is the second derivative. And then just to kind of, again, reinforce the fact that when you differentiate a function, you get the slope function or the derivative function, and it has a geometric interpretation. And we want to be grounded in understanding what f prime of x represent. And so here's f, and then here's f prime. And again, just to kind of double check intuitively or graphically our understanding of derivative, notice if I pick a point here on the original function and I look at the tangent line, notice the tangent line is horizontal. So the slope is 0. So that means that the derivative of the function at this point is 0 because the slope is 0. And notice that in the orange function, f prime, the value of f prime is 0, which makes sense, right? And notice that over here on the left side, if you look at my mouse, all the tangent line has negative slope. And so notice that on the orange function, the value is negative because it corresponds to the slope of all the tangent lines. Whereas if you look on the right side here, the blue function, all the tangent line have positive slope. The function is increasing. So notice that the orange line also have positive value. Something we're going to see later, a little bit more later. Okay, so we learned about the power rule, and we learned about the exponential rule, and we want to make sure we don't confuse these. If the variable is in the base of this, then that's the power function. Like for example, x squared, right? The variable is in the base. If the variable is in the exponent, then that's the exponential function. For example, 8 to the x, right? If the variable is in the exponent, then that's the exponential function. We have to make sure we know the difference so that we can apply the correct rules. Okay, so let's kind of see some example to make sure that this is really clear. Okay, here we go. So notice that here's a kind of a power, right? We have an exponent, you have a base. Notice that the variable is in the base. So this is just a polynomial, this is just a power function. And this is just the power rule. Bring down the 5, minus, take the exponent, minus 1, which is 4. So this is the very, very simple power rule. Now notice here, the variable is in the exponent. So that this is an exponential function. It's not a polynomial. So to differentiate it, actually, you know what? Maybe I should have showed this a little bit later. But this rule is actually something we're going to cover in a little bit here in the video. But this is a different rule than the power rule. And then the case we just saw, the exponential e to the x. Again, the variable is in the exponent, right? The e is a constant. So this is an exponential function. We know how to do that. This is the function where you differentiate it. It gives you the same thing. So here's another one. Notice that the variable is in the base, and then the constant pi is in the exponent. So this is another example of a power rule. So again, bring down the power, bring down the pi, subtract 1, pi minus 1. So the power rule of these two cases here we covered last week. And this is another case. Again, case 2 here, 5 to the x and pi to the x. Both of them, the exponent has the variable. So those are exponential. But again, those two cases we're going to see later how to do that. So I'll come back to this slide a little bit later. And then another common mistake is that, again, here's the variable is in the exponent. So this is not the power rule. So this is a common mistake to bring down the x minus 1. This is wrong, right? This is not the power rule. This is the exponential rule that we'll cover a little bit later in this video. In fact, later what we're going to learn is that when you differentiate, if you differentiate e to the x, it's the same as e to the x. But when you differentiate where the base is not e, if the base is something other than e, it turns out to be a little bit more complicated. It's still the same. It's still exponential e to 2 to the x, but it have an extra constant ln of 2 next to it. And so again, more on that a little later. Okay, here's the product rule. It says that if I want to differentiate a product of two functions, then again, this is a common mistake for this is to differentiate them separately and multiply them. That's actually not correct. If you differentiate the product, we have to use the product rule, which is that here's the f of x with the first function, g of x with the second function. So you take the first function, you leave it alone, and you multiply by the derivative of the second function. Plus, you take the second function, g of x, leave it alone, and you multiply by the derivative of the first function, the derivative of f of x. So it's a little bit more complicated. You have to make sure you memorize this. But the mistake is to think that you differentiate them separately and multiply them. So that's not true. You have to do this full product rule. For example, if you have x times e to the x, notice this is a product, and we want to differentiate to find f prime. Again, the mistake is you don't want to differentiate them separately and multiply them. You have to apply the full product rule. And so the rule is that, so the f of x, the first function is x in this case. G of x is e to the x. So the product rule says that first you take the first function, you leave it alone. Take the first function x, leave it alone. Differentiate the second function. Differentiate e to the x. Plus, then you take the second function, e to the x, leave it alone. Then you differentiate the first function. So this is the application of the product rule. But differentiating e to the x is simple. It's just e to the x. Differentiating x is just 1. So the final answer is this. Again, you can either leave this. In fact, if you just remove the 1, that would be the valid final answer. Or if you want, you can factor out e to the x. So either of these answers are acceptable. So this is the product rule. And then the next rule is called the quotient rule. This is when you have a quotient. You try and differentiate a function divided by another function. And this rule is a little bit more complicated than the product rule. And it is that you take the bottom function, g of x, you leave it alone, you differentiate the top function, minus, notice the minus, you take the top function, you leave it alone, you differentiate the bottom function, and then you divide everything by the bottom function square. Notice this is a little bit complicated, so let's do an example. Another notation that people might be helpful to memorize is this one, is that you try and differentiate a quotient. So it's the bottom times the top prime minus the top times the bottom prime divided by the bottom square. Another mnemonic you might hear is using this low and high idea. So I don't have the slide for it, but the top is called the high function. The bottom function is the low function, right? It's the low function and then the high function. So again, low is g of x, high is f of x. So another mnemonic is low d high minus high d low over low square. Again, sometimes some students might, if you've done this in high school, you might have heard of that mnemonic. Again, it's low d high minus high d low over low square. If you say that a few times and memorize that, then that can also be helpful to apply this rule. But again, however you want to memorize this. Okay, let's do an example of this. Okay, so here it is, right? Here's low, here's the bottom function. Here's the high function, the top function. So it's low, which is the bottom function, leave it alone. D high, which is differentiate the high function, differentiate the top. Minus high is the top function, the high function, times d low, which is differentiate the low function or the bottom function, all over low square. So yeah, so now when we differentiate the high function, it's just the power rule apply to each of these. So to differentiate x squared, for example, is 2x. Differentiate x is 1. And when you differentiate a constant is 0. And so again, the derivative of this right here is just 2x plus 1. And then to differentiate this, again, it's just the power rule apply separately. To differentiate x cubed, it's just 3x squared. When you differentiate constant, it's just 0. So that goes here. And then the rest is the algebra. That's it. The first step is the only calculus step. The rest is just algebra. And so one way of doing this is to multiply everything out. Use FOIL, right? This times this times that, this times this, and then this times that. You multiply everything out. You distribute everything out here as well. This times this times that, and then this times this. So you multiply everything out. And then, so again, if you multiply this out by using FOIL, you get these 4 terms. You distribute with this, you get these 3 terms, and you combine everything on top. Because this is a minus, you have to make sure you're careful here. You have to minus this term, minus this, and then you also have to minus this. You have to distribute this negative. And that's going to be something that is a lot of students will make mistake on, is forgetting to distribute this negative. So if you do that, if you distribute everything and combine like terms, you get this final answer. So for example, 2x to the 4, right? If you distribute this minus 3x to the 4, you combine like terms. Those are like terms, you get a negative x to the 4. X cubed here minus 3x cubed, that's a negative 2x cubed. 12x minus, actually there's no linear term, so it's just 12x, it's just 12x. And then the 6th term, right, there's no other constant term here, so the 6 just stays as a 6. And then the bottom is being square, right? So leave that. So that's the final answer. Okay, I want to go back to the slide real quick and kind of show you. So we did some of this already. So here's kind of the full table from last week and also this week so far. To differentiate a constant, 0. If you differentiate x to the n, it's just the power rule. Bring down the n, minus 1. When you differentiate e to the x, it's just e to the x. And then last week we talked about if you have a constant multiple, to differentiate that, you just leave the constant alone and differentiate the function. To differentiate the sum of two functions, you just differentiate them separately and add them. To differentiate the difference of two functions, you differentiate them separately and subtract them. And then today we'll learn about the product rule. If you want to differentiate the product, again, it's not differentiating them separately and multiply them. You have to say, keep the first function, differentiate the second, plus keep the second function, differentiate the first. So this is the product rule. And here's the quotient rule that we just saw. Low, g, right? D high, differentiate the top, minus high, d low, differentiate the bottom, over low square. Okay, let's go back to the slide, to the animation here. Okay, a couple more things to memorize. If you want to differentiate sine, the derivative of sine is cosine, and the derivative of cosine is negative sine. So let's do some example. Okay, I want to differentiate x squared times sine of x. Notice it's a product. So I have to use the product rule. So again, keep the first function, x squared, differentiate the second, plus keep the second function alone, differentiate the first. And to differentiate sine, we know that it's cosine, and to differentiate x squared, we know is 2x. So this is applying the product rule, as well as the differentiating sine, the trig function sine. Okay, let's go back to the slide as well here. And then, so here's kind of the rest of the 6 functions, the 6 trig functions that you learn in pre-calculus, and how to differentiate them. So differentiating sine is cosine, differentiating cosine is negative sine, differentiating tangent is secant square. Again, we want to memorize all these 6. To differentiate cosecant is negative cosecant cotangent. Differentiating secant is secant tangent. Differentiating cotangent is negative cosecant square. Again, you do want to have these memorized. I noticed that exactly 3 of these are negative, and the other 3 are positive. And one way to memorize this is to notice that when this is c, if you're differentiating something that has a c, it has a negative answer. So cosine, cosecant have a negative answer, cotangent has a negative answer. Everything else is positive. So that can be helpful. So differentiating cosine is negative sine, right? The c. And then differentiating cosecant, this is negative cosecant cotangent. Differentiating cotangent is negative cosecant square. And these two are kind of similar, right? Cosecant has a repetition, cosecant cotangent. Secant has a secant tangent, has a repetition. And then tangent and cotangent is kind of similar. Differentiating tangent is secant square. Differentiating cotangent is negative cosecant square. So those are kind of similar. That may help you memorize. Okay, let's go back to the animation here. Okay, so here's the quotient rule, and then applying, memorizing the derivative of the 6 trig function. So low d high, so low is 1 plus tangent, d high, differentiate secant, minus high, which is secant, differentiate the low function, d low, and then the low square. Okay, well, to differentiate secant, we saw that it was secant tangent. To differentiate 1 plus tangent, differentiating 1 is 0, differentiating tangent is secant square. So this is applying the quotient rule. And then doing a little bit of algebra can help simplify the answer here. So for example, notice there's a secant here, and there's also secant here as well, so I can factor it out. And then what's left is actually there's actually a couple of things here. Actually, before I do that, let me move back here. There's a trig identity that can help us simplify some of this. So the trig identity is secant square is equal to tangent square plus 1. And so that's going to be helpful for us to simplify this part of the problem. So notice that secant square is tangent square plus 1. And so here we can make a simplification by noticing that if you do tangent minus secant square, this term right here, tangent square minus secant square, if I move things around, tangent square minus secant square is -1. So again, if I move the 1 to the left side here, move the secant to the right side, I get that this right here is just -1. Okay, all right, moving on. All right, the next thing, the next rule is called the chain rule. And this is where it gets a little bit complicated. The chain rule is when you have a chain of function. There's an inside function, g of x, and there's an outside function, f of g of x, and you want to differentiate this. And so the way this works is that to differentiate a chain of function, again, there's an inside function, there's an outside function. First, you differentiate the outside function at the inside function in terms of the inside function, times you differentiate the inside function. So again, this is called the chain rule, and it's a little bit complicated. So we're going to do a bunch of examples. So again, the outer function, evaluate at the inner function. To differentiate that, you differentiate the outer function, then evaluate at the inner function times the derivative of the inner function. Okay, so here's a good example. So the outer function is the square root. The inner function is the x squared plus 1. So you want to think of this as a chain, right? There's an inner function and there's an outer function. So again, this is a little bit more complicated. So one way to think about this is that the inner function is the u function. So is this x squared plus 1? That's the g function. And the outer function is the letter f, is the square root function. So one way of doing this is to kind of you differentiate the outer function separately from the inner function. You have to do two derivatives. You have to differentiate the outer function. You have to also separately differentiate the inner function. So to differentiate the outer function, again, the outer function is root of something. So to differentiate that, it's just the power rule. Again, 1/2, bring down the power. Subtract 1 is -1/2. You can rewrite that as 1/2 root of u. Again, a negative 1/2 is the same thing as you bring it out to the bottom and make a square root. So that's how you differentiate the outer function. The derivative of the inner function is simpler, it's just 2x. And so again, so the way you think about this is that you differentiate the outer function, the square root, you evaluate in terms of the inner function. You plug in the inner function times differentiate the inner function. So notice, when I differentiate the outer function, the square root, I get this. And now I'm going to plug in g of x into that, where u is. So you take g of x, which is the inner function, x squared plus 1, you plug it inside of this derivative. So you plug it in where you plug in where u is. So that's the f prime g of x. Again, f prime is differentiating only the outer function, but you evaluate it at the inner function. You take the inner function, you leave it there, and then you differentiate the inner function, which is 2x, and then you can cancel the 2 here. So that's the chain rule. It's a little bit confusing, so I'm going to give you some more example. In fact, there's another way of explaining this that's a bit easier in a moment. Okay, let's do something, let's just kind of see this. I think this is a better example in terms of inner and outer. So there's an inner function, x squared. There's an outer function, sine. So the chain rule says differentiate the outer function first in terms of the inner function. So differentiate the outer function in terms of the inner function. So here's the outer, here's the inner. So you differentiate the outer. To differentiate sine is cosine. So that's the outer, derivative of the outer, in terms of the inner. So leave the inner alone. Evaluate at the inner function x squared. Then times the derivative of the inner function, which is 2x. So again, differentiate the outer, cosine, evaluate in terms of the inner, so leave it alone, times the derivative of the inner, which is 2x. Okay, here's another one. So what's the inner, what's the outer function? Notice here, this notation, this square means that you square the entire sine function. So the inner function is sine of x. The outer function is the square function. So when you differentiate this, you have to differentiate the square function. That's the outer function. Okay, so here we go. The outer function is the square. So first you differentiate the outer function, which means you use the power rule, bring down the 2, right? Evaluate, bring down the 2, subtract 1. So bring down the 2, subtract 1 is a 1. But you evaluate it in terms of the inner function. So you bring down the 2, subtract 1, means that you leave the sine of x alone. Times the derivative of the inner function. So when you differentiate the inner function, the sine function, you get cosine. So there it is. There's another example of the chain rule. So now I'm going to explain the chain rule in terms of the power rule. So you're combining the chain rule and the power rule. And this is kind of the easy way of doing it. Earlier I did the example, the first example of the chain rule. I think this is kind of the easy way of thinking about it. So we're combining the chain rule and the power rule. Now we have a power, the n power here, and then there's a chain, there's an inner function u. So the way you do this is that you bring down the n, subtract 1, and then you differentiate the inside function. So again, you have another way of saying that is that you have a function to the n power. It's a power rule, but there's an inside function. So you bring down the n, you leave the inside function alone, you subtract 1, then you differentiate the inside function. So I think this is kind of the easy way of seeing it. Again, you do the power rule, you bring down the n, you leave the inside function alone, subtract 1, then you differentiate the inside function. So this is how you apply the chain rule that has the power rule as the outside function. So the inside is the g of x. Okay, here we go. So here's the inside function. Here's the outside, the power function. So to differentiate this, you do the outside first. You do the power rule first. Bring down the 100, and then subtract 1, 99. But you leave the inside function alone. It's all in terms of the inside function. It's all evaluated at the inner function. So bring down the power, leave this inside alone, raise to the minus 1 power, 99. Then you multiply by the derivative of the inside function. The derivative of x cubed minus 1 is just 3x squared. So that's it. That's how you apply the chain rule, power rule. So again, bring down the 100, minus 1, leave the inner function alone, then differentiate the inner function. And then this whole thing is a product. Here's another one. Notice this law is a quotient rule, but if the top is a constant, if the top is a function, then this is definitely a quotient rule. But if the top is just a constant, and then this is a root or a power, then you can rewrite this as a power, and it's much easier to apply the power rule than the quotient rule. So again, the quotient rule is the most complicated, so whenever you can avoid it, you want to avoid it. If you see a quotient, but one of either the top or the bottom is a constant, then typically you can rewrite it as a power rule. So notice I can rewrite this as the bottom raised to the negative 1/3. Again, cube root is the same thing as 1/3, and because it's at the bottom, I can put it on top as a negative 1/3. So we've seen this before last week, where you have when you try to differentiate root, that is in the denominator, you put it on top as a negative power, and then you apply the power rule. It's much easier than applying the quotient rule. So the first step is not calculus, it's just rewriting. Notice this is the same function f of x. I'm rewriting this original function as to the negative 1/3 power. Now I can apply the power rule, chain rule. Bring down the negative 1/3. Keep the function the same, the inside function the same. Minus 1, negative 1/3 minus 1. You gotta be careful with the fraction here. Negative 1/3 minus 1 is negative 4/3. And then differentiate the inside function. And so to differentiate the inside function is just 2x plus 1. And so this is the final answer. So again, rewrite as a power, a negative power, and then apply the power chain rule combination. Bring down the power, subtract 1, negative 1 minus 1, be careful with the fraction, is negative 4/3, and then times it by the product, by differentiating the inner function. Okay, this is a more complicated one. Notice that this is again a power, the outside function is the power, so you know it's a power rule, but there's a chain rule because the inside function is a complicated function. So remember that here's the quotient rule again, low d high minus high d low over low square. But that's just part of the problem. The full problem is the power rule and then the quotient rule. The inside function is the quotient. So when you differentiate the inside function as part of the chain rule, you have to use the quotient rule. So here it is. Again, the power rule is the outside function. So bring down the 9, leave the inside alone, subtract 1, so it's 8. Now differentiate the inside. Again, that's the chain rule. Differentiate inside is a quotient rule. So to differentiate this is a quotient rule. So now I have to apply the quotient rule. And that's exactly this right side, orange side right here. Low, d high is 1, minus high, t minus 2. d low is just a 2 over low square. And then if you multiply things out and simplify on top, 2t plus 1 times 1 is 2t plus 1. You distribute the negative 2 here. 2t minus 2t goes away. 1 plus 4, right? Distributing this is 5. And so this is like kind of the power rule, but with a quotient rule inside of it. Okay, here's another one. This one is a little bit more complicated. Notice that has the product rule. There's a product. And then within the product, there's also the power chain rule. So this is kind of a more complicated one. Again, make sure you remember the product rule is keep the first the same, differentiate the second, plus keep the second the same, differentiate the first. So notice that this whole problem is a product of two power chain rule, right? So first you have to apply the product rule first. So to apply the product rule, again, keep the first one the same, differentiate the second. That's this orange right here. Plus, keep the second one the same, differentiate the first. So this first line is just the product rule. So we're not doing chain rule yet. The product rule is the main rule first. This is, first of all, a product, right? So okay, again, keep the first the same, differentiate the second, plus keep the second, differentiate the first. Now, to differentiate the second, though, notice this is the power rule chain rule that we just learned. How do you differentiate this? Bring down the 4, subtract 1, leave the inside function alone, times differentiate the inside function. So this right here, this color part, is differentiating this part, which is power chain rule. And then notice again, bring down the 4, subtract 1, differentiate the inside. So this is, you have to differentiate this as the next step. Plus, and then to differentiate this, again, this is another application of the power chain rule. Bring down the 5, subtract 1, leave the inside alone, subtract 1 is 4, then differentiate the inside. This is differentiate the inside. So the next step is another step of differentiating. So to differentiate this is differentiate the inside of the chain rule earlier, is 3x squared minus 1. And differentiating this, it's just 2, right? This is 0, so it's just 2. And then we just combine everything in fact, here the way we do is we just factor some of the components out. There's a common factor here, 2 times 2x plus 1 to the 4 power, right? There's 5 of these here, and then there's 4 of these. So you take out 4 of them. That's that. There's a 2 here, and there's also a 2 here. Take that out. And then there's 3 of these, and there's 4 of these, so you take out 3 of them. So you take out this whole expression here. You look at my mouse, this whole expression can be factored out. And so you factor it out, and then whatever's left here, we can simplify it by multiplying everything out. So again, you distribute everything inside of here, then you get this term right here. And this is the common factor we pull out, and it stays the same there. And then this part right here is just simplifying this by distributing and combining like terms. Okay, and so now we learn about the exponential rule as the first rule we learned in this video. So now let's do it with the chain rule. So notice this is a chain rule because there's an inside function, the sine function. There's the outside function, the exponential. So you have to use the chain rule here. Right, so the outer function is the exponential. The inner function is the sine. So again, how do you apply the chain rule? You differentiate the outside function, the e to the x. And that's easy, it's just e to the x. But you evaluate it at the inside function. So that's this part right here, the first part here. Differentiate e to the x, that's just e to the x. But you evaluate it at the inside function, so you plug in the sine of x. And then you differentiate the inside function. To differentiate the inside, you differentiate the sine, which is cosine. So there it is, that's how you differentiate an exponential that has an inside function. Again, differentiate the outside, e to the, differentiate e is just the same, it's just e to something, but you evaluate the inside, so you say e to the sine of x, and then you differentiate the inside. Okay, here's another one. So this is what I mentioned earlier, when earlier I showed you that table and I said that I was kind of a bit ahead of myself. Differentiating e to the x is just e to the x. But if the base is not e, if the base is different than e, then it's also just b to the x. It's the same as the exponential, but it has an extra constant next to it. It's ln of b. Notice if b was e, then ln of e is just 1. And that's why you get that special case. So this rule really applies to e to the x as well. But in the e to the x case, if b was e, ln of e is 1, and you get e to the x, the easy case. But if b is not e, then you have to make sure you don't forget the extra constant. So for example, right, again, if this was e, the answer would be e to the x. But because it's 2, it's e to the x, it's just 2 to the x, the exponential stays the same, and then you have the extra constant ln of 2. And then this case is a little bit more complicated. The inner function is a function, so this is a chain rule. So you have to use the formula 5, the exponential case, and the chain rule. So the outer function is 5 to something. So to differentiate that, you have to use the formula number 5. And notice that to differentiate 5 to the something, it's just 5 to the something times ln of 5. Again, that's formula 5. Again, differentiate the outside function is you leave the exponential alone, and you put an ln of 5 next to it. Then you differentiate the inside. The inside is x squared. So now you have to differentiate x squared, and that's just 2x. Okay, that's it for this week.